After studying this module, you shall be able to know about the various types of inorganic pollutants, understand what is meant by acid mine drainage, learn about the heavy metals present in water bodies, from where they come, why they are toxic, how they are toxic, and we'll also get a brief idea about radioactivity pollution. This category of water pollutants consists of inorganic salts, mineral acids, finely divided metals, compounds of metals, heavy metals, metal complexes, etc. There are various sources through which these substances can enter natural water bodies. For example, metallurgical industries, smelting, chemical industries, mine drainage, and some natural processes. We will start with discussing the most harmful of the elemental pollutants, that is, heavy metals. Heavy metals are amongst the most harmful of the elemental pollutants present in water and are of particular concern because they are dangerous to humans. These elements are generally transition elements and some representative elements in the lower right-hand corner of the periodic table, like lead and tin. Now, all transition elements are not toxic. For example, iron is an essential transition element and it is beneficial for us. Among the heavy metals which are toxic, mainly are cadmium and mercury among the transition elements. Most of these form bonds with sulfur groups in enzymes, resulting in disruption of enzyme function. Protein carboxylic acids, which contain carboxylic group COH and amino group NH2, also get chemically bound to heavy metals. Cadmium, copper, lead, and mercury ions bind to cell membranes, disturbing transport processes. Starting with cadmium. The solubility of cadmium compounds in water is affected by the acidity of water and the nature of the source. Cadmium enters water from industrial discharges and mining wastes. Cadmium is very similar to zinc and undergoes geochemical processes along with zinc. It is present in the +2 oxidation state. The level of cadmium is higher in areas supplied with soft water of low pH. Acute effects have been seen where food is contaminated by cadmium. Acute cadmium poisoning in humans has very serious effects. Severe gastrointestinal upsets, bronchitis, emphysema, anemia, high blood pressure, and kidney damage have been reported. Generally, cadmium replaces zinc and other divalent cations essential for functioning of certain enzymes, thereby altering its structure and impairing its catalytic activity. Itai disease has been a case of mass cadmium poisoning in Toyama Prefecture, Japan in 1912. This cadmium poisoning caused kidney failure and softening of bones. The disease caused severe pains in the joints and spine. The cadmium was discharged into rivers by mining in the mountains. The mining companies were later sued for the damage, but not before the extensive damage caused to humans. Itai disease is one of the biggest pollution-associated diseases that occurred in Japan. Lead. Several industries and mining processes are responsible for exposure to inorganic lead. It is present in the +2 oxidation state. Lead from leaded gasoline used to be a major source of atmospheric and terrestrial lead, much of which eventually entered natural water systems. This problem has been solved now by using unleaded gasoline. In addition to pollutant sources, lead-bearing limestone and galena, lead sulfide, contribute lead to natural water. In aquatic systems, lead has been found to be quite toxic to many organisms, even at small concentrations. Acute lead poisoning in humans causes severe dysfunction in the kidneys, the brain, liver, reproductive system, and central nervous system, and causes sickness or even death. Nowadays, lead is not a serious pollutant in drinking water, except in those cases where lead pipes are still being used. Mercury. This metal generates a lot of concern as a pollutant. It is discharged into natural waters from industrial effluents. Metallic mercury is used as an electrode in the manufacture of caustic soda and chlorine, and in laboratory vacuum apparatus and thermometers. Industries like batteries, vapor lamp fertilizers, pesticides, etc. also use mercury compounds. Mercury has a great tendency to bioaccumulate in the form of methyl mercury and shows a greater capability of biomagnification through food chains. Because of their resistance to degradation and their mobility, the alkyl mercury compounds are generally considered to be more of an environmental threat than either the aryl or inorganic compounds. The toxicity of mercury was tragically illustrated in the Minamata Bay area of Japan during the period 1953 to 1960. A total of 111 cases of mercury poisoning and 43 deaths were reported among people who had consumed seafood from the bay that had been contaminated with mercury waste from a chemical plant that drained into Minamata Bay. Metalloids. The most significant water pollutant in this category is arsenic. It's a naturally occurring element found in the Earth's crust and within many ores. It is released to the water bodies through industrial smelting and natural processes like soil erosion, weathering, and mineral leaching. The toxicity of arsenic compounds is well known since ancient times. Arsenic occurs as organic and inorganic compounds in drinking water, and the inorganic forms are more toxic than the organic ones. The toxicity also depends on the oxidation state. Arsenic 3 compounds or arsenites are 10 times more toxic than arsenic 5 compounds or arsenates. Arsenic gets accumulated in the tissues and causes gastroenteritis, skin lesions, skin cancer, and multi-organ system failure. The toxicity is mainly due to the deactivation of enzymes containing thiol groups as arsenic binds to this group. It also adversely affects generation of ATP and coagulates proteins. Water pollution due to arsenic is noted in West Bengal, some northeastern states of India, and in our neighboring country, Bangladesh. The situation in villages of Bangladesh has been classified as a real disaster, and the arsenic levels in tube well water range from 0.05 milligram per liter to 10 milligram per liter, which is well above the WHO maximum permissible limit. According to reports published by WHO and UNICEF, arsenic has been labeled as a ticking time bomb, and the disaster in Bangladesh will be more serious than the Bhopal gas tragedy, with as many as 85 million of its 125 million population being affected by it. The diabolic situation of the two nations is a result of years of negligence. While setting up tube wells in these two nations, the responsible organizations had not paid enough attention towards the quality check of underground water and did not even conduct tests for arsenic. The toxic effects of some pollutants are summarized in the table. Now, this table shows the toxic effects of some inorganic pollutants. The table is self-explanatory, and obviously, as the term suggests, most of these pollutants have adverse effect. They are poisonous. We have already discussed the toxicity of arsenic as well as cadmium. Now, ammonia, ammonium hydroxide and ammonium salts, these are also toxic, and toxicity increases with increase in pH. The toxicity to fish increased by 200% when the pH was raised from 7.4 to 8. Calcium is antagonistic to lead, zinc, aluminium, and toxic solutions of sodium, potassium, and magnesium. In case of chlorine, the toxicity increases with decrease in pH. Chlorine combines with thiocyanate to form a non-toxic effluent to a toxic one, converts parathion to a more toxic form, paraoxone, combines with phenols and ammonia to form chlorophenols and chloroamines, both of which are toxic in nature. The fluoride toxicity increases with decrease in pH, and fluoride causes fluorosis, mottling of teeth enamel, nervous and skeleton disorders. Copper is at a high pH above 7. The toxicity is reduced because copper hydroxide precipitates out. Cyanide and hydrogen cyanide are toxic. Below pH 8, hydrogen cyanide is in undissociated state, and the toxicity increases 2 to 3 times with rise in temperature. Toxicity also increases with fall in oxygen, and it is highly toxic with zinc and cadmium. Mercuric chloride, we've already discussed the toxicity of mercury. It is synergistic with small amounts of sodium chloride. However, the effect is antagonistic with high concentrations of sodium chloride. Lead is synergistic with calcium and a cumulative poison. Sodium ferrocyanide, sodium sulfide, sulfuric acid, they are all toxic in nature. Zinc is not highly toxic. The toxicity increases with increasing temperature and decreasing oxygen. The toxicity decreases with increasing hardness. It is synergistic with nickel cyanide and copper, and its toxicity with cadmium becomes additive. Acid mine drainage. This is also a common problem, and it is damaging for the aquatic environment. Somehow it may be considered to be similar to acid rain. Coal mines discharge substantial quantities of sulfuric acid and iron 3 hydroxide, that is ferric hydroxide, into local water bodies. On exposed coal mine surfaces, minerals containing sulfur, mostly iron pyrites, come into contact with air and water, forming sulfuric acid, and this is carried into streams by waters from the mine. Iron sulfide is stable in absence of air, but in presence of air, during mining operations, oxidation reactions occur and produce large amounts of sulfuric acid. The first equation shows the reaction of iron sulfide in presence of water and oxygen. It's solubilized to give ferrous ions, and the ferrous ion undergoes aerial oxidation to give ferric ions. The role of microorganisms are important in the overall process. The rate of these reactions is slow at a pH below 3.5, but in presence of thiobacillus ferrooxidans bacteria, the rate of the reaction increases. In the pH range of 3.5 to 4.5, The reaction may be catalyzed by acid-tolerant iron-oxidizing bacteria, ferric ions, produced in the reaction discussed earlier between ferrous sulfide with water and oxygen, dissolves the pyrites further and constitute a cycle for the dissolution of pyrite, which is shown in the equation. Acid mine drainage is the primary source of pollutants that increases the acidity of water bodies. This adversely affects thousands of miles of streams and has been one of the most significant causes of water degradation. The acidic water is toxic to plants and animals of an aquatic ecosystem. It also damages biological productivity. Alkalis discharged by industries such as textiles, tanneries, and coke oven operations can destroy aquatic life. Radioactive pollution. Radioactive pollution is caused by the harmful radiation from radioactive materials like uranium and thorium. The sources of radioactive waste are mining and refining of radioactive materials, waste from nuclear power plants, industries, and medical waste. Many radioactive wastes are lethal at relatively low concentrations and in minute amount may be mutagenic. A typical uranium ore contains about 2 to 5 pounds of uranium oxide per ton, so that large amounts of ore are processed for extraction of uranium. As a result, large quantities of uranium tailings are produced, which pose the problem of radioactive pollution. Radioactive substances can enter the human body by food and water and get accumulated in blood, in organs like liver, in the thyroid gland, bones, and muscular tissues. These radioactive materials cause mutations leading to skin cancer, leukemia, and they also damage the reproductive system and reduce the effectiveness of certain enzymes. Radium and thorium are chemically similar to calcium, so they get absorbed by the bones. Similarly, cesium-137 is chemically similar to potassium, which is a common constituent of all living cells. Cesium from fallout passes to man through contaminated meat and dairy products. In the Colorado River Basin, the concentration of radium increases to about double the maximum permissible value for human consumption. Based on the concentrations of radioactive elements in water body, wastewaters may be classified into 3 categories. Low-level waste. Wastes that are within specified concentrations of radioactivity may arise from the non-nuclear or nuclear industries and typically consist of everyday items that have become contaminated during contact with radioactive materials, and waste from decommissioning operations such as building, rubble, soil, and metal items such as framework, pipework, and reinforcement. These wastes may be solid, liquid, or gaseous and have very low productivity and are produced in large volumes. In general, such wastes are disposed easily through careful packing and burying. High-level wastes. These wastes are usually liquid or solid wastes having very high level of radioactivity and released in low volumes. These wastes cannot be released into the environment without treatment. In general, they may be stored above ground for several years and subsequently buried. Intermediate level waste. These wastes are also in liquid or solid state with high radioactivity. They are released in low volume with proper treatment. Measurement of radioactivity. Radioactivity can be measured in terms of radiation emitted or in terms of radiation absorbed by an organism. It is expressed in terms of Curie abbreviated as CI, rad and rem. The becquerel BQ measures the activity of the radioactive source, that is the number of atoms which within a particular time frame transform and emit radiation. 1 becquerel is equal to 1 emission of radiation per second. 1 curie is equal to 3.7 into 10 to the power of 10 disintegrations per second. The parameter Gray measures the absorbed dose, meaning the energy transferred to the material by ionizing radiation upon encountering it. 1 Gray is 1 joule per kilometer. 1 rad is 100 ergs per gram. The sievert, that is SV, defines ionizing radiation defect on living material. Contrary to the becquerel, the sievert is a very large unit and we often use submultiples. 1 m sievert equal to 1 millisievert, which is 0.001 sievert. A factor called quality factor is used in human health to measure the relative effectiveness of different radiations to produce some biological effects. This is measured in terms of dose in rem, which is dose in rad into RBE. For gamma and beta radiation, 1 rem dose equals to 1 rad, and for alpha radiation, 1 rem dose will be equal to 20 rad. We now summarize what we have learnt up to now. This module was generally devoted to water pollutant by inorganic substances. Inorganic chemicals of many types enter water from municipal and industrial wastewaters and as a result of urban runoff. Acid mine drainage is the primary source of pollutants that increases the acidity of water. On exposed coal mine surfaces, minerals containing sulfur come in contact with air and water, forming sulfuric acid, and this acid is carried into streams by waters draining from the mines. Harmful radiation may be released in the environment from the wastes of uranium and thorium mining and refining from nuclear power plants and from industrial, medical, and scientific utilization of radioactive materials. Cesium-137, the radioactive isotope of cesium, is very chemically similar to potassium. Potassium, you all know, is a common constituent of all living cells. Cesium from fallout passes to man through contaminated meat and dairy products. Large amount of water is used for cooling purposes in various industries. This, when discharged into water bodies, causes thermal water pollution. Many heavy metal ions are highly toxic. We have already seen cadmium, mercury, lead to be extremely toxic. They have a very high affinity for the thiol group and they deactivate enzymes. A metalloid arsenic is extremely toxic, present in groundwater, and if the situation is not controlled, we will all be at a massive threat. Japan has borne a lot of problem of water pollution due to mercury and cadmium. Itai disease and the Minamata disaster are well known, all caused by irresponsible behavior of the agencies which indiscriminately discharged effluents into the water bodies.